Okay, so I'd like to talk about the exponential of a matrix. So the exponential of an m by n matrix is given by this definition. We use k here. Now, of course, the first thing that we need to check is that this makes sense. The right-hand side makes sense. Okay, so we could use the operator norm and use the fact that the space of m by n matrices equipped with the operator norm is a complete space. We could do that, but we can just do it like this, right? So if we want to show that this converges, right, let's show that the absolute value is bounded above, right? So the idea is that let's look at the ijth entry of this right here and show that it is finite. Or if you like, or if that's a bit uncomfortable, essentially what we're doing is we're taking the sequence of partial sums, which is a sequence of matrices, and we show that the ijth so each entry of the matrix Bn does not, that is bounded above by something finite for all n. So let aijk denote the ijth entry of the matrix that is a to the power of k. Now we're going to bound this above by, of course, the maximum value of the entries of a. So let little a denote the maximum of the ijth entry of the original matrix A. Okay, the absolute value of that. And of course this maximum exists because I and j are between 1 and n. Okay? So we notice that, we can bound each of these guys above by something in terms of a, right? So if we look at aij1, obviously this is bounded above by a. If we look at aij2, this is equal to the sum of aij times by, aik, yes, it's bounded above by this, okay, which is bounded above by n times by a squared, right? Because you can bound each of these guys up above by a squared and you're just summing up to n. Right? What about this? Well, this is sum over k1, k2 of aik1, k2, k3, ak3, j. Okay. Again, this is bounded above by now a cubed, right? Times by, now this is going to be n squared, right? Because if you freeze one of these k1 index, you get an n, and you get an n appearing for each value of k1, and there are n of them. So clearly it's going to be n squared a cubed, right? Now clearly, just continuing this pattern, you can bound it above by this, okay? So now, let's go back to the original sum. Okay, so we're taking a sum to infinity, and this is just, so this right here makes complete sense, right? This is just a sum of numbers in the sense of analysis, right? Regular analysis. And of course these can be complex valued, of course, right? So everything works if all the entries are complex valued. Now this is less than or equal to, just from the triangle inequality, this, right? And then this is less than or equal to nk plus 1 a to the k over k factorial. Okay? Now we just have to show that this sum converges. But if we just look at this carefully, this is the same as 1 over n, which I can take to the front. And then this is just na to the power of k over k factorial. So that's just nothing but, and in fact I can forget about this 1 over n, right? Put another bound. And this is just the exponential of n times a, right? Which is sort of what we'd expect, right? Because when we were computing if you compute the matrix exponential of a diagonal matrix, then it's the exponential of the diagonals. All right, so this is sort of how you'd expect this. So for any a that's a linear map from Rn to Rn, i.e. an m by n matrix, exponential of a is well defined. All right, cool. Now what we're working up to, right, is we want to prove the following. Okay, it's gonna take a bit of work to get there, but what we're aiming for is this theorem that if A is an m by n matrix, okay, then what we want to show is that the solution to the initial value problem dx dt is equal to a times x, where x is a vector in Rn, or it could be, I guess, Cn, all right, or Kn, and A is an m by n matrix. If you have a linear system, you can write the linear system like this, with, of course, subject to the initial value. This is given by x of t is the exponential of t times a times by x naught. And moreover, this solution is unique. So this is what we're aiming for. Now, how would we prove this? Well, we'd have to differentiate this, right? But so we have to think very carefully about how you differentiate this matrix product with respect to t, right? So let's talk about that, right? So we get to the three fundamental properties of the exponential matrix, okay? So let A, B, and T be n by n matrices, okay? First fundamental property is that this helps us, this fact we use to compute, if B is T inverse times A times T, right? I guess we have to say that T is invertible. Also, it must be in the hypothesis. So if B is equal to this, then that implies that the exponential of B is T inverse exponential, matrix exponential of A times by T. Now this is particularly useful if we can write an exponential A in the form of T inverse dt, where D is a diagonal matrix, because this can be, the exponential this can be explicitly written down. Okay, what's the second fundamental property? The second fundamental property is the idea about, so with the regular exponential, there is the property that the exponential of a sum is the product of the exponentials. Okay, but this is not necessarily true for the matrix exponential. If A and B commute, then exponential of A plus B is the exponential of A plus the exponential of B. Okay, the reason for this is that if you look at the power series of the exponential from real analysis, or from regular old analysis, then to derive this property you implicitly use that you can swap the product of a and b around. But of course that's not necessarily the case when you've got matrices. So third fundamental property is that exponential of a is invertible, and the inverse is given by exponential minus a. Right, this is true even if a is not invertible. Okay, proof. So okay, so what's the proof of this? So the idea of the first one is that t inverse a t, right, to the power of k is t inverse a to the k times t, right? This is because if you square it, for instance, the middle terms involving the t's always cancel, and you're left with a squared, and you can repeat this. So this is fairly easy to see, okay? And also, of course, you've also got t inverse a plus b times t is equal to the sum. Okay? So, if we look at right, so if we look at b is equal to t inverse at, right, and if we take the sum b to the k over k factorial, and let's go up to a finite term, right, this is then equal to, well, this is equal to, so, okay, so like I said, this is t inverse a to the k t over k factorial, okay? And then from this property right here, this is nothing but t inverse times this sum times t, and then take the limit as n goes to infinity, which you can do because we've already talked about convergence. Alright, so what about now the exponential of a sum is the product of the exponentials? So here's the important idea. It goes back to the binomial theorem, right? So if we were to look at exponential of a plus b, this would involve the sum of a plus b to the power of k over k factorial, right? And you'd have to show that you could split the sum like that, right? Now, we've got that ab is equal to ba, right? So, a plus b to the power of k is equal to k factorial times the sum over j plus k is equal to n of a to the j over j b to the k, or k factorial. Okay, why is this the case? So sorry, this is correct. All right, so the binomial theorem gives us this, and then we can rewrite it as this double sum over I plus j is equal to n. So we got this. Now our claim is this following statement, that we can separate this sum right here into a product of ai's and j's. If we're taking this sum, sorry, I should really say sum from n is equal to 0 to infinity. Because, then this is exponential of a and this is exponential of b, right? And you'd be multiplying them together. Okay, so what's the proof of this? We know that each of these infinite series of matrices converge, so we have no issues with that. We just have to check that they're actually equal to each other, right? Now what we do is we define the partial sums given by the sum from n is equal to 0 to 2m of And since, these guys converge, you can go to infinity in any way you want, essentially. We could have taken S of 3m, we could have taken anything we wanted, really. Okay? So let's look at this. Alright? And let's define alpha of m to be this, beta of m to be this to be this series. Okay, just going to write it with a different dummy index. And we define this. So this is our definition of S, this is our definition of A, alpha, and this is our definition of beta. Okay? So, what we want to show is that S2m minus alpha m beta m goes to 0 as m goes to infinity. Okay? Alright. So let's define, we define the norm of m to be the maximum norm, right? Because, there are different ways to define the operator norm, right? And they're all equivalent. You've got all the way up, from the one norm to the infinity norm, and they're all equivalent for finite dimensional spaces. So it's convenient to talk about the infinity norm of m, right? So we just take the maximum of the entries. Okay? And so in this norm we want to show that the difference goes to 0 as m goes to infinity. Okay? So this is going to get a little bit messy, but let's just do it. Okay? So if I take S of 2m, right? Okay, so let me take the norm of S of 2m minus alpha m beta m. What am I going to get? So this is going to be, alright. Okay, I'm going to skip the proof of this lemma. I'll make another video going through it, but it's quite difficult. So next proposition is that suppose that V, which is an element of Rn, is an eigenvector of A, right? And it has an eigenvalue lambda. Okay? And the claim is that V is also an eigenvector of e to the A. Right? And its eigenvalue is e to the lambda. Okay? You can see this very clearly if you just look at, a diagonal matrix again. So when we looked at mu naught lambda naught, then we see that 1, 0, and 0, 1 are eigenvectors, and the exponential of this matrix, well, since it's still diagonal, 1, 0, and 0, 1 are still eigenvectors, but the eigenvalues are now e to that. So the proof of this is that, well, let's look at e to the a times v, okay? And we assume that av is equal to lambda v. Well, this is equal to, right? And then this v comes in, okay? Now, if v is an eigenvector of a, right, eigenvalue lambda, then if we look at a squared, well, that's going to be a times av, which is a times lambda v, which is going to be lambda squared v. And so continuing that pattern in the obvious way, we get this. So it's lambda to the k times the identity matrix times v, but yeah, we could just write it like this. Right? We're just taking a sum of vectors now. And we can take the vector v out of the sum. And this is just a regular, this is a regular exponential of a number. So this is v times e to the lambda. So we have that e to the a, matrix exponential of a, times v is equal to e to the lambda times v. Okay, so let's look at the function e to the ta, right? So this is a function that sends t, which is a real value, to an element of m by n matrices, or linear maps. So e to the ta. And we can identify this with r to the n squared. So really this is just a map from r to rn squared, right? So we can talk about derivatives we can talk about derivatives easily. So I claim that d by dt of the exponential of t times a is nothing but a times exponential of t times a, which is also equal to this. So you can commute this product of two matrices. Okay, what's the proof? Well, we have to look at the definition of the derivative. So if we take the limit as h goes to 0 of exp, so this is going to be exp of t plus h times a minus exp of ta, and divide by h. Well, this is going to be exp of ta plus ha minus exp ta, and of course these two matrices clearly commute with each other, right? So I can write it like this, right? So we really have to use the property that, we have to use the characteristic property of the exponential. And then, well, we can take this guy out, and then we've got limit as h goes to 0 of exp ha minus the identity matrix over h. Okay, but the definition of exp of ha is ha to the power of k over k factorial, right? From some k is equal to 0 to infinity, right? And this is just the identity matrix plus h times a plus, and then higher order terms, right? And I'm dividing by h. The i's cancel, and I'm just left with a, therefore. So this is exp of ta times a. Now, I was a little bit careless when I factored out, right? So how do I know I can factor out to the left? What if I factored out to the right? Well, the reason is really, okay, so there's kind of a hidden step that we have to be a little bit careful about, right? I wrote this as, so I factored out exp ta from the left. Okay? And then this h came inside, right? And this is all perfectly legal. Now, I could have split this up like this instead. Right? Then what would have happened? Well, then we'd have exp ha minus the identity times h, and then the exp of ta would be on the left hand side, and then the limit would just be applying to this guy only, right? It would be kind of incorrect to take this outside the limit, because you'd be assuming that they commute. Well, they do commute, but more properly speaking, you'd write it like this, right? But the fact that the fact that these two guys are equal follows from, essentially, that you can write exp of a plus b as exp a times xb, or you can write it as xb times exp a. Okay, so now we get to the big theorem. Right, so what's the big theorem here? So we want to show that we want to show that exponential of ta solves this, okay, is a solution. So if we take d by dt of e to the ta times x naught, right, this is going to be equal to, well, the d by dt acts on this guy only. Okay, so why is that? Well, again, if you want to be really careful, you can think of this as a map from r to rn squared, if you like, right? But the point is that we've shown that this is a times e to the ta times x naught. That's the important bit, right? We've shown that the chain rule sort of still holds, okay? Now, we've got that e to the, so if we look at, so if we call this x of t, right, we've also got that x of 0 is indeed x naught, right? That's trivial, okay? Now, to prove uniqueness, what we say is suppose y of t is yet another solution, okay? Then we set, and satisfying the initial value problem, let's set z of t to be e to the minus ta times y of t, okay? Then if we look at z prime of t, then you can show that this is equal to 0 for all t. That's quite easy. So that means that z is a constant, okay? And so, since it satisfies the initial condition as well, we get that z must actually equal x for all t. And that's the proof, right? That's how you prove it's unique now.